Hello, and welcome to today's webinar, 7 Ways to Quality Control Data in Real Time. I'm David Ferguson from Aquatic Informatics, and I'm today's host. We're happy to bring you guest speaker Derek Forsbloom, who is the hydrometric supervisor for the Northwest Territories at Water Survey of Canada. Also presenting today is Alistair Foreman, product manager, Aquatic Informatics. To start today's webinar, I'll take a few minutes to share some trends from our recent international industry survey that highlight the importance of today's presentation. Derek will then share 7 ways that Water Survey of Canada is systematically correcting its continuous water data. Alistair Foreman will be sharing tools in Aquarius that can be used to automatically produce timely and high-quality information from large volumes of continuous data. There will be about 5 minutes or so at the end of the webinar to take questions from participants. At that time, you can use the Q&A console in WebEx to ask questions, and you can do that throughout the webinar. Any questions not addressed during the Q&A, we'll make sure that we get back to you following the webinar on those questions. Over 700 people participated in our recent online survey, and it highlighted some important trends that relate directly to today's presentation. All of these trends point to more data being generated and the need to make data processing more efficient. Networks are growing. We're generating more continuous data. We're seeing more real-time data. We're seeing production cycles are being shortened. And commercial software like Aquarius is being adopted because it is part of the solution to these problems. Ultimately, smart and proactive hydrometric managers like Derek and forward-thinking organizations like the Water Survey of Canada are finding ways to focus on higher value data analysis, not tedious manual data workup. Let's take a look at some of the examples that I'm referring to. Water resource managers forecast the size of their networks to grow by 53% more monitoring stations over the next decade. This tells us that more data is definitely coming. And when we look at continuous data, the report confirms the rapid adoption of monitoring technologies that generate huge volumes of data. For example, digital multi-channel data loggers are used today by 71% of respondents, and solid-state electronic sensors are used by 67% of respondents. Real-time data transmission. With more continuous data being collected, water resource managers are also turning to real-time communications technologies for transmission. Respondents expect satellite communications to grow from 16% of stations in 2002 to 40% of stations by 2022. Web-enabled sensors are expected to grow from being used in 4% of stations in 2002 to 40% in 2022. So huge growth. And on production cycles, today consumers of hydrological data want immediate access to continuous information that is quality controlled. Tolerance for data faults and dynamic data has declined. Demand for metadata and higher value analysis has increased. Quality controlled data is expected to be published sooner, as we can see here. The report also shows that sophisticated data management software is increasingly being adopted to handle the real-time operations and increased demands of these hydrometric programs. We see that 23% of respondents are using actively licensed commercial software. These respondents reported being better able to meet evolving stakeholder expectations for real-time data product and services, metadata availability, higher level analysis, and timely reporting and publishing. The comprehensive report is available on our website, but as you've seen, the amount of data is growing rapidly, and the industry is finding ways to better manage the production of quality-controlled hydrometric information. Derek Forsbloom is here to tell you about some of the valuable things they are doing at Water Survey in this area. Derek has been with Water Survey Canada for the past 13 years. Seeing the need for real-time, quality-controlled data, he co-wrote an application called RTQ, Real-Time Discharge, which allowed the computational process to be automated and QC'd in real time and then sent to stakeholders. 3 years ago, Derek worked with the AI implementation team to implement Aquarius into daily operations, replacing RTQ. When Derek is not engineering new ways to better quality control data, he can be found at his remote cabin watching the northern lights, and I think we have a picture of that right here. I'm now pleased to welcome Derek Forsbloom. Derek?
Thank you, David. As mentioned, my name is Derek. I work for Water Survey of Canada. And for those, most of you probably know what Water Survey of Canada is. It's a federal agency mandated to monitor water quantity in Canada, and we've been doing that since 1908. It's a Department of Environment Canada, and we have over 2,500 stations in Canada, most of them transmitting real-time data. But myself, I work in the Northwest Territories and Nunavut District, so our operations are somewhat unique, perhaps like Alaska or Yukon, in that many of our stations, or most of our stations, are aircraft access only, so very remote, and we don't get to them very often because of the high cost. Then you add on top of that there's no power out there, so we use solar power systems, 12-volt systems, and we transmit the data on the GOES satellite transmissions. But what is interesting, the developments in the north, is we have this transitioning client expectations. 20 years ago, our data was almost solely used for historic basin studies and whatnot. But that's not only the case today. We're seeing much more interest in real-time data. Well, why? Why is there that interest? Well, there's always been a universal interest in quality data. But now that the data is coming in 24/7, what's changed is the user expectations of that data. And what hasn't changed is that everybody wants good data, and we have to defend our data. And what we're finding is we had to make decisions quicker about our data. And the two illustrations in the slide here give a bit of an example. You know, the one on the left is telemetry coming into our office. Well, if that telemetry is being scrubbed up and down the river, as you can see in the green line, 20 years ago we would just sit down, compute it, and come up with the corrected blue line. And then we would produce discharge from that. Well, what's happening now is, if you look at the next one, if we do nothing, if we delay the decision of changing that data, the red line becomes our discharge that we're producing because of the GOES real-time data. Well, that's unacceptable, and we had to change our operations. And previous to 2006, how we changed our operations was we fixed this manually, just more often. Then, as mentioned, we had in-house software for a few years, and now we're having Aquarius help us manage that real-time data. So what I call that approach before was more of the traditional approach. We had data coming in, we didn't know what to do with it, but we knew we had to compute it. So our answer was to manually compute it with an increased frequency. We worked up the data, whether it was monthly, weekly, even daily, depending on our client needs. And that is in contrast to what I like to call the ever-evolving approach to data in quality-controlled real-time fashion. And that is to use software. Use software to compute the data on the fly and use the technologist to manage what the software is doing. And an analogy I have used is comparing it from a rowboat to a motorboat. You can get where you want to get to in a rowboat, but it's a lot more work. So if you can use a motorboat or speedboat, well, it's a lot easier, it's a lot more fun. So what is our motorboat in computational software in real time? Well, if the motor is action, and the steering of the boat is information or input from the user, then what our motorboat computational software would have to do is it would have to be powerful enough to do these things. It would have to identify and remove erroneous data. It would have to be able to apply known corrections. It would have to assume or forecast those corrections forward until you can go visit the station and a different number can be obtained. And then it would have to be able to go back and update the data back to that point. It would also have to inform the technologist what it's done or what action he or she should perhaps do. It would have to inform interested parties, clients, internal management, when something of interest has happened. And it would have to do this 24/7 in real time. Oh, and one other thing, it's got to do it as efficiently as possible. So, that's all. That's all it has to do. That's a significant workload for software. And the steering wheel on your boat would be the technologist. He would use this power to direct the computational software to gain efficiencies in computations. Well, in Aquarius, the way that this analogy comes together is the information or the steering component is your notification toolbox in Aquarius, and the action or the motor part is the data correction toolbox in Aquarius. Now, these two toolboxes are independent, so they're not tied to one another. The intermediary between these two is the technologist, and he sets the parameters as to which are triggered on each of these. And the goal is to have these two independent toolboxes work together in real time so that this hydrometric computational real-time ship gets to the destination. So the objectives of this presentation is to look at ways we can meet this ever-evolving level of service and quality expectation. It's not really meant to be a policy discussion in that we're saying this is what you should do. More, this is what you can do, or this is what we have done here in the North to address our client needs for real-time quality-controlled data. And we're going to look at some tangible examples of what we've done mostly in this year and last year with the Aquarius software. Now, what we've done is we use somewhat of a multi-pass approach. In other words, we set up our QC settings, and the first one is more of a permanent, broad brush type of setting. And what it's going to do is it's going to clean your obvious errors. It might miss some, but it's going to clean some, and it's going to let us know that we may have to investigate. And then we may have a second or third closer criteria setting that is behind that we may have in a seasonal situation or under certain conditions. So you kind of have this first sweep of data and then a second sweep. And this is where the Aquarius differs from our previous. So our previous had actually 8 passes on the data, but they were rigid. You couldn't change them. Aquarius, there's an infinite number of ways you can approach the QC on your data. And as we get into our examples, you'll see what I mean. But what we expect, that's the software. What we expect the technologist to do is to evaluate the situation, to make an approach on the QC, to analyze, correct it, and then evaluate again and do that again, this multi-pass, until he gets to the point where they're happy that what the results are what you want. So then, of course, we want the software to input or to work with the direction that the technologist gives. So what we're going to do is look at a few 7 examples of data manipulation in real time using the Aquarius software. And the first one is about as basic as you would get, because in this situation we're not really asking the software to do anything per se. We're just setting up. It's more of an information for station management purposes. So in this here is in the notification toolbox. And what I've done in this picture here is I've set up a notification when a system that is under solar power and battery power. And what I've done is I've selected the signal, the voltage telemetry signal, and I've named the notification low VB or low battery voltage. And I've sent the email to myself, and the trigger, if you see, is on a pen, so as the data comes in, I want this to be actioned. Well, it could have been on any signal that I chose. I could have chose nitrogen pressure or signal strength, or it could be stage record in a certain zone that I'm looking to obtain a discharge measurement. In this case, I chose battery voltage under 12. You can see it here that when you select the notification, a window pops up and allows you to set the criteria of that amount. So in this case, when a signal or telemetry is incoming with less than 12 volt, I get an email that says 3 points less than 12 volt were appended to the data set. Of course, the reaction, we're not asking the software to do anything with this information. The reaction is actually external of the software. So the reaction is station management. We go put a new battery system or an extra solar panel, whatever the case may be on the station. So that's probably your most basic of real-time information. It's not in computations, but it is extensively used with station management internally within our organization. But let's look at some examples where we're asking the software to actually do some of the computational work. Well, this example here is a remote northern river. The situation is just after spring breakup, and if you see in the picture there, the technologist is taking pictures. That ice is jammed up over 25 feet deep. So you cannot get, you can see as far as you can see on either side of the river, there's ice jam up. There's no way you can get on the water. And in fact, it's quite a difficult station to operate. And coincidentally, it's also one of our more scrutinized stations, where people want to know what's happening in real time. So what we've done is we've had this multi-sweep or this multi-parameter QC setup. We have a constant, permanent QC setup that we use here. And then we have ones that, under different conditions, we will set up or turn on or off. And what's happened in this picture is the line into the river has been ripped out. That ice has just ripped this line out, so the gauge is not operational. What the technologists are actually doing here is they're going to take a block with an orifice line and throw it over the ice into the river. So it's a bit primitive, but it's worked. So let's take a look at that first QC pass. Here's the QC parameters that are set up. The first thing you'll notice is the stage values. What we're saying here is anything above 8 or below 3 is not valid. They're not valid. Let us know. Remove them from the data set. The next is the rate of change. If this river goes up more than 2 meters a day or falls faster than 2 meters a day, let us know. It's of interest, and or, depending on the settings, it's invalid. Do not stop. Take it out of production temporarily. A third QC setting that's set up here is spike or value-to-value control. And this is very powerful. It's my favorite of the QC settings. And this is basically what this is saying is if there's a change in the values greater than 50 millimeters over an hour from value to value, remove that value from that time period. And I'll show examples of that. And this here is almost essentially the opposite flat line. So if it doesn't change more than 1 decimeter in 3 hours, then something's wrong with the gauge. Stop producing real-time data, or email me and let me know. And the final thing about this is that I've selected use corrected data. And suffice to say for now in our discussion, that what that means is any corrections I've applied to that data set, apply them and then run the QC filters. So if there's a lines being scrubbed, or if there's a datum that you're assigning to that, assign that first and then run it through the QC data. So what's happened at this gauge? Well, our technologists have thrown the line over the river and then gone back to the office. Well, a few weeks later, the water's receding, and what's happened is it's come out of the water. You can see on this flat line here that the gauge is just reading atmospheric pressure at this point, and the data is not valid. So the QC settings have picked this up and removed the flat line area from the first arrow to the second arrow. An email was triggered that this was being done, sent to the technologist. They arranged for a trip, they went out, and by this time we were able to reset a line by boat, which is where the data is picked up in the bottom. But what did the QC settings do with the data? Well, you can see in this slide that the green it represents the removed produced line. The flat line was taken out with the flat line correction, and when the line was reset, there was some erroneous values bumped in there, and it was removed with the spike parameter. So what's been left is good data. You could have, and then the other, if you look just a little further down, you can see the orifice line has been scrubbed a little bit, and that spike has been removed because it's too big of a variance there. So what did we ask the software to do? Well, we had an alarm trigger in notifications for flat line. That was triggered, first of all, when the line came out of the water. An email was sent to the technologist. He would have anticipated at some point the line would be out of water, and he would have actioned that. The data correction at the same time removed that erroneous data. text went out, they reset the line, the spike threshold in data correction was triggered. When they were resetting, that data was removed. So what was left was valid data. The incorrect data was removed. The only thing we could have done here is we could have chosen to fill those data gaps with the data correction toolbox on a linear basis or on a cubic spline basis. We didn't in this case. But that's what the software did. The technologist, his job here was simply to review the data, well, to receive an email, review the data, review the effectiveness of the QC settings, fill in a gap, and then as brought out here, there was an orifice movement that he would have noticed and received an email for, and he would have applied this correction of 114 and carried it forward to when they could reset the line. So the software did most of the work. Let's look at another example. This is the same river, and what was happening here is satellite transmissions were overlapping. And it's the same QC settings that we've set up on a permanent basis. And this one was, this particular one that triggered was this spike setting that I like so much. It's 50 mils over 1 hour. Well, this one was a bit of a head scratcher because if you look at the stage record here, you can see the water level is increasing and then it starts to go sporadic. So this site also suffers from silting quite bad, so we assumed it was that, but it became pretty evident, and we were looking at the data and saying, well, it's removing quite a bit of it, but it became pretty evident that that's not what it was, and it almost looks like the data split. Well, that's quite a unique set of coincidences, because what happened was another group had used our DCP ID and was transmitting, and just by sheer fluke, the numbers at the when they started transmitting were very similar to the numbers that we were recording at the time. So you can see this data starts to diverge. So we didn't really know at first what it was, but within a day or two we started to figure out, and we realized that the bottom line was the correct line and the top line was incorrect. Well, as you can see here, that's pretty much garbage data as it's coming into telemetry. Well, how did our spike correction clean this up? Well, here's your answer. Very well. So it was able to, once we made a slight modification to the spike, looking for the bottom part of the line, it was able to clean that data up with absolutely zero human interaction beyond the initial QC settings. So for those that do manual deletion of data and manual computation, you can see the time saving to have had arrive at work in the morning, and this is done for you. So what did we ask the software to do here? We set up the standard QC settings for that station, and the spike thresholds were triggered in notification, and data was removed in data correction when at the beginning of that blending of the two signals. We couldn't quite figure out what it was, so the technologists reviewed the data, and within a day we realized that the lower one was the correct one. So we made a second swipe we changed the adjustment to look to the lower part of the trace in the data correction toolbox, and from that point we really did nothing other than monitor. The data correction cleaned it up as it was incoming, and the data was cleaned. And if you just go back to the signal, if you can read the timestamps, it actually was from July to November. We weren't able to correct this telemetry signal for 4 months, but there was no rush to do it because the data was being cleaned as quick as it was coming in. There was no operational requirement to panic to get out there, even though this station is heavily watched and scrutinized, because the client wasn't seeing that. The green line was completely omitted from data production. Let's look at another example. This is a regulated stream. Again, another heavily watched stream because there's a power dam just upstream. And the water license indicates that if the water level goes below 3 meters, they have to open the spillway. So they're very conscious of this, and they want to know if the corrected water level goes below 3 meters. Well, you can see in this example that that's happened in the circled part of the diagram. So we could set up a notification wherein the water level goes below 3, and it's emailed to us, and then we could phone the Power Corp, or we could send a notification directly to the Power Corp via email that the data has gone below 3. Well, that's certainly more efficient to let them know that directly and CC ourselves. But do you really want to have data going out that you maybe don't have a high level of confidence in? Well, here's something we've done to increase the level of confidence because many of our clients do receive direct emails in our office. They're used to real time. We've worked with them for years with it, and they're used to receiving emails. And this is by adding a second parameter in the criteria. You can see here that instead of saying any of these parameters that would indicate trigger an email, I'm saying all of these parameters. So any values below 3 meters, and go down a little bit further, 3 meters, and the water level cannot change more than 25 centimeters in a day. If it changes more than 25 centimeters, it's probably something going on in the site. And hold off sending an email. Send me an email, but not the client an email. So in this case, because the data here looks like good stage record, the data would have been sent to the client. But let's look at another, so again, just what did the software do? Well, below 3 meters and a rate of change within acceptable values, emails generated, sent to the client. Really not asking the technologist to do anything other than review the validity of it when he gets to work in the morning. But let's say in that same situation that it's 2 o'clock in the morning and some vandals have pulled the orifice line when they're having a party on the river, and you receive these stage readings below 3 meters. Well, would that same email be sent to the client? Well, no, it wouldn't, because the rate of change was be too high and it wouldn't be included in that amount. But the technologist would receive an email, the office would receive an email, because if you look at the original parameters, it's a lower level of 3 and a spike of 50 millimeters in 1 hour. So that orifice, that pulling the line, would generate that. So an email would not be sent to the client, but it would be sent to the office, and the data would be removed from production until the technologist could take a look at it. So that's basically what this summary talks about, is that the email is sent to the technologist, and until that period of time, the rate of change of so many values of so much time has passed, data production would temporarily be removed, until you had a chance to take a look at the data. But here's where we talk about some of the efficiency gains, because what if we ask the technologist to do at 2 in the morning? Well, nothing. Like it says, hopefully he's sleeping and not the one pulling the line. The data is being corrected while this technologist is asleep. And at 8 o'clock in the morning, when he gets to work, he finds that there's received an email. He looks at the data. He realizes that there is an orifice movement of 1 meter. He applies an offset correction in Aquarius from the point of the movement forward. That correction is then applied to all incoming data. The data is computed back to the point of the movement, and it falls within the parameters, so no further triggers, alarm triggers, are triggered. So really, the data has been corrected, and life goes on, and there's been nothing out of the ordinary that we've asked the technologist to do, and yet the data has been computed and corrected in real time. Let's take a look at another example. This is sometimes a very difficult thing to compute in real time, and that's silting. And we have some of our sites that have silting problems. The data can start to vary quite greatly. So at this site, we have a secondary notification set up, a second swipe as you were, and it's already queued up in the system. It's not turned on all the time, but we have it set up there. And it's essentially the second pass, and all it says is if the values are more than 10 millimeters in 1 hour, remove them. Let us know and remove them. So here's some silting record. Now, if you're familiar with silting, what happens is that the orifice tip gets plugged with silt. The pressure builds up in a nitrogen system, gas purge system, and the water level starts to it reads an erroneously high water level, and it does that, increasing and increases until it builds enough pressure to blow the line clean, and then you get likely a fairly valid reading, and then the whole system starts to build pressure again. So we used to have to remove these values by hand. It takes a lot of time, and certainly in real time, it can give you some very erroneous record. So this QC parameter that we set up to do a second swipe looks for the bottom of this signal here. Well, here's what it looked like in real time with no technologist intervention as the record's coming in. Now, this is, somebody could look at this and say, well, I'd like to change a bit of this record. But the reality is, for something that has had no human intervention, we find this to be within 1 to 5% of the approved record set. It's very good considering that it's done as the second the data comes in, this QC is run on it, it's cleaned up and published to our real-time site. That did an excellent job of cleaning up this data. Again, what did we ask the software to do here? Well, there was a permanent notification of 50 mils in 24 hours. It was enough silting that it triggered that, but it wasn't enough to clean up the data. But the email was generated, it was sent to the technologist. He was made aware that silting was then an issue. The technologist investigated, finds silting's an issue, turns on the secondary QC settings based on a minimum deviation, and then he added a data fill gap. So as data is removed, the gap between the two valid points is filled on a linear basis, like you see in this picture. The software's action then is just to simply continue to remove the spiking data in real time and fill the gaps as it comes in. And when the silting and the line is reset, or if the silting stops, we simply turn off this secondary parameter. Let's look at it. Here's a seventh example. This here is a system failure in a submersible transducer system. It's actually working intermittently, but you can see that a lot of the values are erroneous. The permanent QC, or the broad, wide brush, is picking up some of the erroneous values, but not quite enough that obviously some of them values are erroneous. So you don't have a high level of confidence that what's going on to your real-time web page is cleaned. Well, it's because it's not cleaned. So it's enough, though, that an email is sent to the technologist. What he did here was simply modify, just a slight modification by adding a second parameter that cleaned it, did another tighter clean through the data, and was able to clean up all the erroneous data, did a very good job on the fly. From this point on, no human intervention. He did this fairly quick, within a few hours of the email being received. But what I wanted to show you here is a close-up of that data being removed. If you look at that highly fluctuating down and up part of the data, you'll see there's a buffer. There's valid data on either side of it that has been removed. So what the software is doing is, as data is coming in, it compares that data, depending on how long of a time frame you've asked it to review. It's going backwards and looking at the time frame and the magnitude that you've set as allowable. So you're always going to be a bit of a buffer on either side of your erroneous data, but that's okay. That just means that the software is doing its job, and it's removing any of the data set that is outside of the parameters you've set. You can see here it's done a very good job. It's for the most part, the technologist may or may not decide to fill those gaps in, and your data set's done. So again, what was asked to do here? Basically, in a nutshell, the QC settings were enough to identify problems. They weren't enough to clean the data 100%. So these were modified. A second one was added. Fill data gap correction was added, and the software took it from there and picked up those erroneous values and removed them, and it did it in real time. So that is the summary of water level data. We could have done the exact same thing manually by sitting down and computing the data every day, and it would have gave us the same results, but it's very inefficient. And if you remember what we talked at the beginning, efficiencies, there's this ever-evolving expectation, and if we want to meet it, our software has to be able to do those 6 things. Identify bad data, remove it. Apply corrections, assume those corrections forward, update the data when there's a new value of correction, inform us of what it's done, inform interested parties of what we tell it to inform them, and do it 24/7 and be efficient in doing it. And what we want the technologists to do is not to manually work up data every day, but to direct computational software. The result of that is that when data is incoming, we can have a high level of confidence that the water level data is correct. And we've done it in an efficient manner. So what we found in the north is that primarily quality-controlled real-time data, as far as software is, we use our software, it primarily focuses on this incoming stage record. And what we found is that if we can fix the stage record in real time, and we're generating flow off of a base curve, we can have the same high level of confidence in our discharge numbers. However, the challenge in producing flow in real time comes from deviation from the base curve, as you no doubt likely know. So whenever we see ice cover or scour deposition, weeds, something thrown into the river, animal activity, weeds, beavers, anything like this that deviates us from the base curve, that's where the challenge comes in real-time quality-controlled discharge. But what we've also found is because of the interpretive nature of these model changes, we have some of the best software available to us to do this on the fly, and that is people. Because high-level analysis like this is fun. No one finds it boring. Low-level data deletion and editing is boring, and it can be cleaned up in the software in stage. So if we do that, what we've done is we've left more time and energy to do this high-level analysis. So we're going to take a look at what the software can do in discharge and what people can do in discharge. So there is things software can do to help you produce discharge when it's off of the base rating. And some of these are notification things like minimum thresholds, air temperatures below. You may expect icing, or if it's a submersible, water temp is a good example. There's other things that we can do with compound notifications. And I find these types of things are ever evolving in our industry. But for example, at one site, we have a velocity index profiler, and it's below a dam. And what we're looking for is a combination of when the stage goes up, but velocity does not go up correspondingly, is an indication that we're under, that the curve or the base model's changed. Or a water level has gone up and the precipitation gauge hasn't gone up, would be an indication that there's perhaps a beaver activity or a constriction on the control. Things like notification, software is very good at that, at giving you information that can indicate a backwater or a change in your base rating. So that's what software can do. But what people can do is apply what they know of the station characteristics to produce better data. So let's take a look at exactly what is meant by that. How can we estimate changes to our model in real time and have a high level of assurance, confidence that the data is within a certain percentage of accuracy? Well, one thing we've done here is we've used historic shifts and channel dynamics as guides in producing discharge. So what this example is, you can see the red is the base curve. And you can tell by the measurements taken that the blue line, there's a bit of scatter when the station is under backwater throughout the various summer. I think this one here is a beaver activity for measurements taken. But what we've said is that basically where the blue circle is at around 9.5 meters, that's flood stage, and whatever shift is applied is washed out, and we're back on the base curve at that point. So what we've done is we've taken an estimation. We've asked our technologists to evaluate what would be a likely shift at the beginning of that backwater event. He's applied it, and then a few days later, a few weeks later, he obtained a shift, or a measurement, and he adjusted that shift. So it's gone from here down to here. So he now has based the shift on a known number. He forecasts that forward, or maybe even assumes it's going to change forward until he gets another measurement, and then adjusts and keeps refining that refining that through the season. Now, the caveat is that sometimes that is ever fluctuating, and it's station to station. But here's an example of a site that we did that. You can see at the beginning, the red line is the corrected stage through the base rating. The orange line is the historic, and then after measurement, assumed forward shift on the data set on the corrected water level, and the blue is actually the final approved data for that record, for that station for annual publication. So you can see that the corrected water level through a base rating isn't going to give us the answer we want, because our measurements have deviated off the base rating at this point. So with the historic, you can see the first segment there, we were a little bit low. We were actually a little bit, the actual final data was a bit higher of discharge. But after that first measurement was taken, in this particular station, we actually were pretty close from then on in. It starts to deviate towards the right of the screen. Another measurement was taken, and it was fairly close to the remainder of the season. So basically what the technologist did here is he used his best available information he had and estimated what the shift is. He applied that to the model in real time. He went and took a measurement. He corrected that number. He evaluated, is it going to stay the same? Is it going to change a little bit? And he repeated this process throughout the season. Now, that may seem like a lot of work, but he's also not doing any water level cleanup at this site. So it's a trade-off, higher level analysis instead of low level data editing. So what kind of shifts could this apply to? Well, here's three that we've found, three different shift mechanisms in Aquarius that we found work in the north, for everything from the smallest creek, mountain, rivers to large Mackenzie River, Mississippi River-sized water rivers. And if you look at the one on the left, this is a shift that we've estimated and just refined based on a measurement for weed and algae growth, or perhaps a constriction in the stream. And if you look at it, what it's done is the blue lines in both of them indicate the level of stage where any shifting would be washed out due to it being a flood stage. So it's basically back on the curve. And this point is the maximum intensity of the shift. And you can see there's a measurement there. So we've gone from flood stage through the shift to what we think would be the maximum deviation to the shift. I think in this case it's about 0.013 meters of a shift there. And then the bottom part on that top left one is where the water level's so low, the flow's so low that it's basically the constriction is not affecting it, and it's back on the base rating. So the same principle applies. This will be an estimate. We use that until we can get a measurement. We get a measurement, we adjust our estimate. We use that until we get another measurement, we adjust our estimate, and basically we're producing the best level, data we can produce with the known numbers we have. The bottom center picture is constriction control. Same example, just slightly different shift. Flood stage at the top there, it's washed out. Bottom stage from here below, the constriction is going to have the same effect on the rating, so it stays the same. And the only part that you have as a technologist requires interpretation is the magnitude. You know the channel dynamics, so it's the magnitude, and your first measurement will give you an idea of the magnitude of that shift. The third one on the right is ice cover. Now, perhaps that's unique to northern United States and Canada, colder climates, but it's the same principle. We, in Water Survey of Canada, we have addressed this by we estimate the shift. When we get a measurement, we apply that shift to the entire range of stage. So that's why this shift doesn't go back down to flood stage, because it's just applied across the entire curve. The whole curve is shifted to the left in this case. But as the measurements come in, we keep refining that and updating that in our discharge model. So those are three unique shifts that can be applied. So what's the value in this discussion? Well, if I had to summarize real-time computations, it would be that producing quality-controlled water level data 24/7 is completely achievable with modern software. The software is very good at identifying and correcting erroneous values. We gain the efficiency in software by not rowing the boat or manually doing things, but by steering software. And by doing that, we allow more time for greater analysis of data, the higher level stuff, producing discharge in real time. Now, that's more of an art, but if your stage data is correct, and you're left with this higher level, this energy and time to do the higher level analysis, it's possible. It's more fun, and it's ultimately what the technologists, the knowledge of the station they have, the knowledge of hydrometrics, hydrology that they have, is using that to a greater avail than removing a obviously erroneous data point. But through all of it, through all of this, what has remained the same since 1908, when Water Survey started monitoring water data and creating discharge, is that the need for quality data remains. So through whatever software you use or whatever process you use, the what hasn't changed. What is constantly changing is the when, the user expectations of when. And so what has to follow that is an ever-evolving level of how that we as hydrometric computers or water managers approach our computations and our products to our clients. And in a nutshell, software, in our experience, has been a great help in gaining the efficiencies needed to focus on this higher level computations. So do what you do best, and that is compute data and let the computer do the rest, which is the menial tasks that it can do. So I thank you very much for your opportunity to speak on these points.
Thank you, Derek. That was really, really interesting. Hello, everyone. My name is Alistair Foreman. I'm the product manager here at Aquatic Informatics. It's extremely gratifying for us to see tools being used in such exciting ways. Derek, I especially liked your analogy of the rowboat and the motorboat, although in your case I think dog team and snowmobile might be more apt, but we certainly got the point, and it was a very good presentation. Thank you. I'm going to speak a little bit about the tools that you saw Derek using from the Aquarius perspective. I'm going to just give an overview for those of you who aren't familiar with the system of how Aquarius manages data, just to help contextualize the messages that Derek was giving. So let's get right into it. The main way that Derek was talking about working with the data was setting up these things he called notifications. And the notification rules that you set up in Aquarius are watching the data as it comes into the system in real time. And there you saw all the different ways that they can detect data that you care about, thresholds and rates of change and spikes and flat lines and so on. And these rules, they set flags on the actual data points, which are the ones that trigger the rule. They don't change anything. They don't do anything. They just mark the point as being suspect. And then, as you mentioned, there's a second thing that can happen. At this point, you can go in and deal with the problems by manually examining the data and doing either not changing it or changing it as appropriate, or you can set up these things in Aquarius called open-ended corrections, which are ways to remove the data and then replace it with an appropriate algorithm. And Derek mentioned a few like cubic splines and linear interpolation and so on. So these are the two tools that Derek was mentioning. And the corrections, either automatic or manually, are done in the correction toolbox. This is what that looks like for those of you who are unfamiliar with the system. Aquarius maintains a copy of the raw data for all time. It never, ever deletes the raw points, which is the green data you can see here. And in this case, there's something wrong with that spike. It's been removed in the corrected signal and replaced with a cubic spline interpolation. And at any time, we can always go back and see the raw data. And in fact, we can switch on and off the corrected data to revert should we decide that the correction was applied incorrectly. And at the bottom, you can see there's a record in Aquarius of the changes that have been made, who made them, when they made them, and a reason for why they made them. So there's a full audit log of all the changes in Aquarius, either manual or automatic. If you look on the far left, you just get a sense there that there's a time range for the correction, and open-ended is one of the options. Now, if we just step back a little bit and think about how all this data fits into Aquarius in the first place, let's just go through some of the capabilities of the system in general, and then we'll get into some Q&A towards the end. The main way that Aquarius manages data is through the concept of a location. Location is a physical spot on the map. This is the map that's part of Aquarius 3.1. And within a location, you set up the details of where it is and what kind of information it's collecting. And we manage Aquarius has a rich interface for managing your measurement locations. Once you have the locations set up and configured that you're going to collect data from, you then go about getting the data out of files into the system or appending them from perhaps a telemetry system into the system. Aquarius has a rich interface to set up file parsing rules for getting data in of all various flavors. Here you can see the contents of a CSV file that we're specifying for the system. So there's many built-in file formats, and Aquarius can ingest a very, very wide array of data types. Once you have the data into the system, you can also bring in measurements, which are discrete sort of field visit type things. Here you can see an example of a bridge measurement that's been made, a discharge measurement. You can bring in all kinds of different measurements, cross-section measurements, discharge measurements, water quality parameter measurements, those kinds of things. And different measurements give different sort of access to their data. Here you can see a discharge measurement that's been brought into the system, velocity profiles and panels and so on. This can come from an ADCP or from a manual weighting measurement, those kinds of things. So now we have lots of data to work with in our system. What we want to do is build some transitions, some models. Aquarius has a very rich rating curve environment for building up stage discharge and any parameter-to-parameter ratings. Derek spent a good deal of time talking about the concept of a shift. So this tool allows you to specify the base curves, transition those curves over time from curve to curve, add shifts, and each of those pieces has a period of applicability to which it applies over the course of the lifespan of the site. The way that Aquarius can actually then derive data in real time is to use those curves. And in fact, there's many other derivation types as well. We can do simple calculations. We can do statistical derivations like converting to daily values or weekly values or max or min or those kinds of things. We can mix data from multiple signals into one depending on various criteria. And we can even access data from outside Aquarius entirely from, for example, the USGS or other sources of public data to bring into Aquarius. Once the data is in and derived, of course, we need to visualize it. The system has a wide variety of ways to visualize data, as you might expect, zooming in and out of graphs, overlaying signals on top of each other, changing their axes, multiple axes, different colors, and so on, and always the physical grid data and the visualization as well. We then have a number of tools for analyzing the data, doing different calculations. We have hydrological statistical packages. Here you can see a flood frequency analysis. We have ways to do windrows plots and all sorts of ways to analyze the data once it's in and been derived. And then finally, it's time to once you've analyzed it, corrected it, figured out what it all means, you need to get it out. And Aquarius has a very rich reporting environment for defining your own output reports and sending them out to various formats. Here, this one's headed to a PDF file. So it's a very high-level overview of some of the capabilities of Aquarius. And I thank you for joining us today. And back to you, Dave.
Thank you, Alistair, for the inside look at Aquarius. We know now that Water Survey of Canada uses Aquarius nationally to manage all of their hydrometric data. We saw good examples of that with Derek's presentation. We wanted to take a few minutes to quickly mention a few other agencies that rely on Aquarius for management of their hydrometric data. In fact, Aquarius software is not just the North American standard, but it is the world leader for water time series data management. You can see here that the world's largest and most advanced environmental monitoring agencies, including the U.S. Geological Survey, also trust Aquarius to manage their data. So we appreciate your time today. Before we do get to questions, a few important notes. You will receive an email following this webinar that includes a number of resources now available to you. So you will be able to get a copy of today's webinar presentation slides. You'll be able to read the survey report, the Global Hydrological Monitoring Industry Trends that we referred to extensively in today's presentation. And you'll be able to watch a video demonstration of Aquarius at your leisure. A recording of the webinar will also be available in about 24 hours. So now we move to the question and answer period. I'd like to invite webinar participants to ask questions of our speakers. As I mentioned at the beginning, you can use the Q&A box in WebEx to enter your question and press send. We certainly do have a lot of questions. We'll get to as many of them as we can. Starting, I think, with the first question for Derek. Derek, how much effort and time does it take to set things up as we saw them today?
Well, as a district, and actually nationally, what we did is we broke the rivers into basic categories and used that criteria as an initial starting point for QC. And to actually set that up, we had the technologists set up their own stations, and it took maybe a few hours to set up their own station list. So anywhere from 12 to 25 stations would be a couple of hours. And then from there, what they do is monitor it and tweak it according to the individual characteristics of that station. And the initial setup was very, very little. Monitoring it and refining it maybe can be done over a course of a few weeks to a few months.
Excellent. Thanks, Derek. Another question, this one for Alistair. The question is, what other kinds of automated activities or things can Aquarius do?
Thank you for the answer is that Aquarius can automatically ingest data. So we have a feature in Aquarius called the hot folder feature, which allows files dropped in specific folders to be automatically ingested into the system. That's a powerful form of automation. The system can also automatically produce reports based on schedules and notifications to inform interested parties in what's going on. Perhaps a regularly daily report would be available for technologists when they got into work every day on their stations. Monthly reports, ad hoc reports based on notifications, those types of things. So those are two other automation examples within Aquarius.
Thank you, Alistair. So the next question is back to Derek. Derek, what kind of efficiencies have you seen in your operations, and have you measured them?
Oh, that's a good question. I think the obvious efficiency is that what used to take us quite a long time to do, and that was data cleanup, especially in the north here with low signal strength in some of our transmissions, has been done automatically. Without throwing a number, I would say probably 90% of the erroneous values that come in are removed by the software. So that's a significant efficiency gain. The other efficiency gain is probably operational. That one example there where 4 months of two conflicting satellite transmissions, you would have had to have chartered an airplane and flown out to that station to fix it a few years ago, but there was no need because the data was cleaning up taking the erroneous value out. So that, in our case, that saved us thousands of dollars. So certainly operationally, that's a great efficiency that we've gained by having QC capabilities.
Thank you, Derek. Our next question is over to Alistair again. Do you need to be a large national agency to use Aquarius?
That's an excellent question, and of course the answer is no. The Aquarius customer base includes the single-person consulting companies up to national governments. The extent to which you use all the automation tools, of course, may vary depending on the size of your organization. But certainly Aquarius is designed to be immediately useful to any size organization.
Thank you, Alistair. I think in the interest of time, we want to respect the amount of time that everyone's given us today, and we appreciate that. We'll end the questions there. We do have a number of other questions that we will answer by email, so we'll get back to everybody with all of the answers to those questions. And just a reminder that we'll make sure you have availability to see the webinar presentation slides. Those will be made available. And there'll be a video demonstration of Aquarius, so you can take a closer look at Aquarius and how it might be able to help you in your operation. Thank you, everybody, for attending today, and enjoy the rest of your day.